When it comes to fighting bacteria, we've got a pretty good playbook. Antibiotics, they're like these incredibly precise targeted missiles. But viruses, well, that's a whole different ballgame. See, they aren't just invaders, they're hijackers. So today, we're going to dive into how we fight an enemy that's already operating from inside our own cells. And that right there is the central, mind-bending challenge of antiviral medicine. A virus doesn't just knock on the door and attack from the outside. No, it gets inside your cells and turns them into its own personal virus-making factories. So the real question is, how on earth do you fight back without, destroying yourself in the process? And there's actually a pretty fancy scientific term for this, an obligate intracellular pathogen. Now that sounds complicated, but it boils down to a really simple and crucial idea. A virus is incomplete. It literally cannot reproduce on its own. You can think of it like a piece of software code that has no computer to run on. So it has to hijack our cellular machinery to execute its program. And that's what makes targeting it so incredibly tricky. Okay, to really wrap our heads around how we fight back, let's use an analogy. I want you to picture each one of your cells as this super sophisticated, high-tech factory. It's humming along, everything is running smoothly, and it's producing all the essential things that keep you alive and healthy. And this is where our villain enters the scene, the virus. And it's not some simple burglar. Oh no, this is a corporate hijacker, an expert in espionage, and it has a very, very specific mission. See, this hijacker's goal is total takeover. It wants to shut down your factory's regular production line and retool the entire operation for one single purpose, making thousands upon thousands of identical copies of itself. This is the heist we need to stop. So how do we stop this heist? Well, our security system has to be smart. It's got to have layers. And the first, most logical step, stop the hijacker before they can even get inside the factory. I mean, it's pretty obvious, right? If the hijacker can't get past the front gate, the whole heist is over before it even begins. This is our absolute first line of defense. And this is exactly what our first class of drugs does. They're called entry inhibitors. Drugs like Meriveroc, which is used for HIV, basically act like a security guard that changes the locks on the building. They physically block the specific receptors on our cell's surface that the virus needs to use as its key, effectively locking it out. No key, no entry. But, what if the hijacker is clever? What if it slips past our security and is already inside? Well, we need a plan B. Because once it's in, that hijacker is heading straight for the factory's main control center, the blueprint room. You see, the virus's genetic code, that's its master plan. And it needs to make tons of copies of this plan to build new viruses. To do this, it hijacks our cell's copy machine, which are the enzymes we use to replicate DNA and RNA. So our next countermeasure is simple. We're going to sabotage that copy machine. And we have two really clever ways to do this. The first strategy is a decoy tactic. We introduce faulty building blocks. These are drugs like zidovudine or remdesivir. They look just like the real thing, so the viral enzyme grabs them to make a new copy. But they're duds. They jam the whole process and bring it to a grinding halt. The second strategy is a bit more direct, the jammer. Instead of a decoy, drugs like efavirenz just stick a wrench right in the machine. They bind directly to the enzyme, changing its shape so it just can't do its job anymore. But hold on, because some viruses, like HIV, have an even more sinister plan. They don't just want to use the factory's copy machine. They want to splice their own blueprint directly into the factory's master schematics. I'm talking about our own DNA. This is how they create a permanent, lifelong infection. Now, to stop this permanent takeover, we use a class of drugs called integrase inhibitors. These drugs, like raltegravir, are incredibly precise. They find the exact enzyme the virus uses to cut and paste its DNA into ours, and they physically block it. The blueprint never gets filed. The permanent infection is stopped dead in its tracks. Okay, so let's say the hijacker somehow managed to copy its plans. Well, the next step is assembly. It has to actually build the new hijackers, and that all happens on the factory's main assembly line. Here's how it works. The viral proteins, they're first made as these long, useless chains, kind of like an uncut ribbon of paper. To become active, they need a special enzyme called protease to act as molecular scissors, snipping them into their final functional parts. And that gives us a brand new target. If we can break those scissors, the entire assembly line shuts down. And that's where protease inhibitors come into play. Drugs like ritonavir are designed specifically to gum up the works of those viral scissors. So what's the result? The new viral particles get assembled with defective, useless parts. They might look like a virus, but they're duds. They are completely and totally non-infectious. All right, so we've locked the door, we've sabotaged the copier, and we've broken the assembly line. But what if a few fully formed functional viruses still get made? Don't worry, we have one last line of defense. Even if a few of these hijackers get fully assembled, they still need to get out of the factory to go attack other cells and spread the infection. So our last trick up our sleeve? We lock the building down, we bar the exits, and trap them inside. This is exactly how common flu drugs work. You know when you take something like Tamiflu? It belongs to a class called neuraminidase inhibitors. These drugs block the enzyme that the influenza virus uses to literally cut itself free from our cell. So the new viruses get made, but they get stuck, tethered to the outside of the cell, unable to escape and infect new ones. So when you put it all together, we have this incredible, multi-layered security system that targets the virus at every single step of its heist. And this isn't just cool science. It matters. It matters a lot. Because this strategy has completely revolutionized modern medicine. It's the reason we turned HIV from what was a death sentence into a manageable chronic condition. It's how we control things like hepatitis and herpes viruses, like shingles. It's what we use to fight the seasonal flu every year. And it gave us absolutely crucial tools like remdesivir during the COVID-19 pandemic. And that's why this field is so critical. I mean, just think about it. It took just one new virus, SARS-CoV-2, to bring the entire world to its knees. That's a pretty stark reminder that this microscopic battle is one of the most important ones we fight. So if there's one thing to remember from all this, it's that antiviral therapy is this masterpiece of strategic sabotage. We rarely destroy the virus directly. Instead, we systematically outsmart it. We interfere with its plan at every single critical step, from the moment it tries to enter, to its replication, to its assembly, and its final escape. But here's the thing. This fight is never really over. Viruses are constantly evolving, constantly changing their tactics to try and get around our defenses. They really are nature's ultimate code breakers. So as they learn to pick our locks and bypass our security, the never-ending challenge for science is to stay one step ahead, to always be designing the next generation of keys to